Alright, so this is the solution for homework 4.3. So let's look at our posts.js file again. So if you remember, we have these three functions. We have getPosts, getPosts by tag, and then down here we have getPost by permalink. So these three functions are what we want to optimize. So we actually want to optimize this query sorting by date. We want to optimize this query looking for a given tag and then sorting by date. And then we want to optimize this query, which is doing a lookup by permalink. So for this example, we're just going to use the Mongo shell to show how to make these queries fast. So if we open Mongo blog, so what this is doing is it's telling MongoDB that we want to connect to the blog database. And first let's do show tables, see what connections we have in our blog. So we have posts, we have system.indexes. So we haven't actually made any users, so we don't have a users collection or a sessions collection yet, but if I had created a user before showing this example, we would see the users collection and the sessions collection here. But right now we just see the posts collection. So the first thing we want to do is try the query for our front page where we show the 10 most recent blog posts. So let's do that. Alright, so this is the query to find the 10 most recent blog posts. So we're not filtering on anything. We are sorting by date decreasing and limiting to 10 documents. So let's see what that looks like. Alright, so these are our 10 most recent blog posts. So our query worked, but let's actually find out how fast it was. So if we go back and run this again, we can do .explain on the end and see how fast our query was. So notice here that n is 10, but n scanned objects is 1,000. So we had to scan 1,000 documents before we could return just our latest 10 posts. So how can we make this faster? So the key here is that an index is sorted. So we can actually just create an index on date, and we can create an index that's either increasing or decreasing. It doesn't actually matter. And MongoDB will know to use that index to find only the 10 documents it needs. So the key to this is that an index is sorted, and we're trying to sort on date. So if we have an index on date, MongoDB can just start iterating our index from the very beginning or from the very end, depending on whether our index is increasing or decreasing, and get all the posts back in the correct order. So let's do that. Let's create our new index and then look at the new explain output. So here we're going to create an index on date decreasing for our query where we're looking for all posts and sorting on date. Alright, so we just created our index. So now let's go back to our query and run the explain and see what the result is. So this is a much better result. You see we have n is 10, n scanned objects is 10, n scanned is 10, and we're using the B-tree cursor instead of the basic cursor. So this is much faster. We have basically sped up this query by 100 times, which is pretty significant. So that's how to make the front page of the blog fast. We need the index on date, decreasing or increasing, it doesn't matter. If you made it increasing, MongoDB would know to start from the end as opposed to the beginning, but I just showed decreasing for this example. So now the next thing we want to do is make the page with the tags fast. So for this, we're going to use our same query, but instead of getting all the documents and getting the 10 most recent documents, we're just going to get the documents for a given tag and then get the 10 most recent documents. So let's actually look for tags Freon. Alright, so this is interesting. So we've run our query filtering by the tags and then sorting by date decreasing, and it seems like we've used a B-tree cursor, which shows that we've actually used an index for this query, which at first seems good, but then we look at the detail and we see that we only returned 7 objects but still had to scan 1,000 objects. So this is kind of a problem. We're still using the cursor, but it's not actually giving us the advantage we're looking for. So why is that the case? Why did we have to scan 1,000 documents before we could return our 7? So the key is that even though we're iterating the index and getting these dates back in a sorted order, we don't actually know until we looked at every document that we found all the documents with the tag of Freon. And in this case, we're returning 10 documents and there were only 7. So we had to look through every document before we could be sure that we have found all documents with the tag of Freon. So how do we solve this problem? Well, what we really need to do is we need to create an index on tags so that MongoDB can actually use the index and eliminate parts of the result set. So again, it's the fact that the index is sorted, and when MongoDB looks at an index, it can say, I'm looking for the tag of Freon. Everything past this point is later in the alphabet than G, so I can eliminate that and just focus on this part and then repeat that process until it gets all the way to the bottom. So basically we need to create an index on tags to make sure that MongoDB can actually efficiently look up tags in addition to sorting on date. But we can't just create an index on tags, we actually should include date in the index as well, so that every time we find a section of the index with the tag we're looking for, we know that that's already sorted. But let's actually just try creating an index just on tags and see what happens. Alright, so now we're creating an index on tags. So we've created our index, and now we can go back and run this query again, looking for the tags of Freon and sorting by the date decreasing. So we run this query and we see that we have n is 7, n_scanned_objects is 7, and this looks good. We've actually used our tags index to efficiently find just the documents we're looking for, and then afterwards we can just sort by date. So I was mentioning before that we should include the date in the index, and the reason for that isn't clear here. In this case, we only returned 7 documents, and there are only 7 documents with the tag of Freon in our whole collection. So it didn't really matter that it wasn't sorted because we only returned those documents and we were able to just get the full result set and then sort it and then return it back. So I want to show the issue here by limiting to something less than 7. So let's run the same query but limit to 5 and then call .explain. So this shows why an index on just tags isn't quite the optimal index for this query. So in this case, we're only looking for 5 documents, but there are 7 documents in our whole collection with the tag of Freon. So we see that n is 5 and n_scanned_objects is 7. So the issue here is that we find all the documents that have a tag of Freon very efficiently. We can find all of those documents efficiently, but when we find them, they're not actually already sorted because we don't have date included in the index. So we find our documents with tags of Freon, and we actually have to retrieve all of those documents, then sort them, then return the 5 latest documents out of the 7 that we retrieved. So this doesn't seem like a big problem now, but imagine we had 500 documents with the tag of Freon. In that case, we'd only be looking for 5 documents. We'd have to get all 500 documents with the tag of Freon, sort them all, just to return the 5 that are the most recent documents. So how can we improve this? Well, the answer is that we want to include the date in our index so that not only does the index allow us to efficiently look up the documents with tags of Freon, but when we find them, they're already in sorted order. So what we want to do is we want to add to this index, making it a compound index, and include date in the index. So we have an index on tags. Now let's make it also on date, decreasing. So we've added our new index. Now let's run that query that wasn't quite optimal. Alright, so these are the results of our query. And notice that, before n was 5 and n_scanned_objects was 7. Now in this case, both of these are 5, because by the time we found our documents with the tag of Freon, they were already sorted, so we could just return the first 5 that we found, because we know they're already sorted in the index. So that's the key, is that the index basically is sorting on the keys that we give it. So that index that we had tags of 1 and the date of -1 basically gives us a structure that's sorted first on tags, and then when we have duplicate tags, like the 7 documents with Freon, then we sort that section based on date. So it's all about the sort order, and this is something to think about, but this is the most optimal index for the tags page. Alright, so let's go to our last index, and that is finding a single blog post. So to find a single blog post, let's just get an example document and get its permalink. So I'm going to do db.posts.find1.permalink. And let me just assign this to a variable, make it easier. So now we do db.posts.find1, and we're looking for a document with a permalink of permalink. And note that neither of these have quotes around them. This may seem a little strange at first, but key names with no quotes are allowed in JavaScript and just mean the key name, but the field name is actually this variable here. So this is a little confusing because I use the same name here, but this is the key name. It's just allowed in JavaScript that the key name is unquoted, and this is the actual variable permalink. So that's going to be this here. It's going to be right here. So if we do db.post.find1, let's just do .title. Alright, we found the title of our document. So now let's see how fast this query is. Let's run the explain output. Alright, so this doesn't work actually. We do find1 on permalink, and then we try to do .explain, and we see we get a type error. So the reason for this is that the find1 is actually a nice wrapper that returns us an object instead of a cursor, and the .explain method is actually a method of the cursor. So to fix this, let's actually do a find and then do .explain. So this should also only find .one document because we're looking based on the permalink. Alright, so this is our explain output. You see we're using a basic cursor, and we're only returning one document, but the number of objects we had to scan is 1,000. So we had to scan 1,000 documents, every single document in our collection, before we could return a single blog post. And this could completely take down your application. So our query is actually scanning 1,000 times more documents than it needs to get the results. So this one's pretty straightforward. We're looking based on permalink, so we want an index on permalink to make this query fast. So let's just do that. Alright, so we've made our index on permalink, so now let's run that query and see how fast it is. Alright, so this looks like a big improvement. So we're doing a find for this one document, and we see that we're using a btree cursor here, so we're actually using an index, and n is 1, n scanned objects is 1. So we only had to look at one document to return this blog page, and so the blog is now much faster than it was before. Alright, so that's the answer to homework 4.3 and how to use indexes to speed up queries for the blog application you've been working with for this course.